today in this section, we are going to look at finding the area of regular polygons. We're going to move away from quadrilaterals and triangles, and we're going to work with regular figures. We're going to see one main formula for regular polygons today, but we are going to do one specialized one, and that is the area of an equilateral triangle. Both of them we're going to derive today so that you can see where it comes from. And then once we've derived it, then you can use that formula. So we're going to work first to figure out the area of the equilateral triangle. So here is our triangle. The understanding we're going to start with is that all sides are equal, all angles are 60 degrees, and that we're going to call the side length S. So each side has length S. And so then what we're going to do is we are going to start with this understanding that area is 1/2 base times height for any triangle. And then our goal is to rewrite this with only S as our variable. So here's what we know. The base has length S, so this is B, and then we need to find an expression for the height. Well, here's the trick. This is a 30, 60, 90 triangle. And so if the side across from 90 is S, remember that's twice the side across from 30, so then we need to divide it by 2. So that would make the side across from 30, which is right here, S over 2. Or you could write it as, if it's easier, 1/2 of S. Either way works. Actually, I like S over 2. So we're going to go with S over 2. And it doesn't want to write. Okay, S over 2. And then if we know the side across from 30, then the side across from 60 is that times root 3. So that makes this S root 3 and then over 2. And in that case, when you multiply something by root 3, I'll do this over to the side. We have S root 2 times root 3. That multiplied number, it does just join the numerator. It doesn't go to the denominator. So it's S root 3 over 2. So here's the deal. Now we know what our height is. So that makes the area coming back over here. That makes our area 1/2 of the base. Well, the base is just our side S times the height, which is S square root 3 over 2. So in order to make this formula usable, what we're going to do is we are just going to multiply different pieces together. Here's what we have. The S's can combine to, we are going to have a fraction, so the S's can combine to make S cubed. And then when I look at the denominators, there's a 1/2 and there's a 2. Well, when you think about denominators of fractions, those will multiply to make 4 and go in the denominator. So that makes this over 4, and the root 3 stays in the top. So with a little bit of cleanup, we get S squared root 3 over 4. So what we've done is we have written the area of the triangle only using S as our variable, and this is our formula. So we'll write this up here. The area of an equilateral triangle with side length S is S squared root 3 over 4. So then let's say, for example, real quick, that our side length was 6. Then that would make the area, we just need to plug in 6 for S. It would be 6 squared root 3 over 4. Let's go ahead and square that. That's 36 root 3 over 4. And we are going to keep this exact, so remember that the 36 and the 4 reduce. And then 36 divided by 4 is 9. And so this becomes 9 root 3. I didn't have to draw anything. I didn't have to find any height. I just have the area, or I have the area is 9 root 3. Alrighty. So next up, we're going to go on to regular polygons. So remember that regular polygons could have any length of sides, but it means that all side lengths are equal and all angles are equal. So we're going to draw a polygon over here. I'm going to draw, that looks good. Alrighty. So I drew a figure and it actually turned out to be pretty regular. So we've got this regular hexagon here, 6 sides. And what we're going to talk about, I'm just going to turn it so that it looks more like this. And there's a couple of pieces here that this figure, it does have a center point that's somewhere equal distance out from all of these sides. So it does have a center that we could draw. And it's got a couple of pieces that we need some vocabulary as we get started here. So first, I'm going to change the color. and I'm going to connect a segment from the center out to one of the vertices. So remember, the vertices are where the sides come together. So this red segment that I just drew, it's going out to the widest point of this polygon from the center. In terms of the regular polygon, we are going to call this the radius. So the radius is the segment from the center to the vertices. So that's the first thing. And so what we can do is, if I connect both radii from the middle to what I just formed some sort of triangle. So I can take this and I could, in this case, if I connected all 6 of these radii, I would make 6 triangles. Next up, in one of these triangles, if I took a segment, what color should we use? Let's use green. If I took a segment and I drop it straight perpendicular from the center to my base, I have just formed this perpendicular segment here, and I have just formed a height of this triangle, and this is going to have a very important, very special name, and we are going to call this the apothem. So the apothem of the regular polygon, you might sometimes hear people call it the apothem. People go back and forth. I'll call it the apothem. And that segment for our regular polygon is going to come into play really important here. And so if we go back to the definition, the apothem of a regular polygon is the perpendicular segment from the center to a side. So it's the perpendicular segment from the center to the side. We're going to think of this as like a special type of height for this polygon. So if we think of this as the height, here's what happens is with this polygon, in this case, I have a regular one triangle, and I could find the area of a triangle. That's something we know how to do. The base is one of my side lengths, and I know what the side length will be, and the height is what we call the apothem. So 1/2 base times height tells us this. Well, if I drew all the other triangles, they'll be the same size. When we work this all the way through, and I'll show you a little bit of the background here in just a second, what's going to eventually come out is people have determined that there is a pattern where the area of a regular polygon comes out to be 1/2 of the apothem times the perimeter. So 1/2 apothem times perimeter. So going back to our hexagon here, let me show you a little bit so you can understand where this comes from. Like I said, the area of one of these triangles, if I call my side length S, it will be 1/2 of the apothem, which is the height, times S, which is my side length. But for this hexagon, I have 6 of them, so the area of the hexagon would be 6 times 1/2 the apothem times the side length. And instead of doing the 1/2 times 6, we're going to rearrange in 1/2 apothem. And this gives us 6 times S. Right now, that would mean absolutely nothing to you, but what is 6 times the side length? That is the perimeter, because there are 6 sides of equal length S, and so that's where our formula comes from. So going back, this is really the most important part, even if I lost you in that. The area is 1/2 apothem times perimeter. So let's see how this looks in a couple of examples here. So now we're going to use this to find the area of a couple of regular polygons. What matters is knowing this little height and then knowing the perimeter. So the first thing we're going to do is find the area of a regular pentagon with a radius of 10. So the first thing we want to do is draw our pentagon. All right, and then what you want to think about is, in this case, the radius will be the length of one of the sides of my triangle. So this is my triangle right here. I know that these side lengths are 10. Now, what we're going to find is there's going to be a really important process that comes into this, and that when I go to draw in my apothem, There are two things that I currently do not know. I do not know how long this apothem is, but guess what? These triangles are not equilateral, so I also do not know what the side length is. And so in order to find the perimeter, I need to know the perimeter. And in order to know the perimeter, I need to know a side. And then I also need to know the apothem. So I have a lot of unknowns here. So here is what's going to come into play. When I think about figuring this out, I need to know something about this triangle. Here's what we can figure out. I can figure out the measure of this central angle. If you have forgotten all the way back to what we did back in our unit on regular shapes and finding all of their diagonals and angle measurements, this is going to come back in play here. But if you forget, we'll think of another way. I want to figure out what this angle measurement is. If I think about cutting it into drawing all the radii and forming a bunch of congruent triangles, I have just formed 5 triangles that are all, if it's regular, that are all going to be the same size. So this angle at the center, or we could think of it as a central angle, is a total of 360 degrees divided by however many triangles we have, which is 5. And so the central angle that's coming out of our center here would be 360 over n, 360 divided by 5. And let's see here. I don't know that number off the top of my head. That, I think, is 72. Let's see. 360 divided by 5 is 72. Awesome. So that means that this angle here is 72 degrees. Now for the rest of our problems, I'm actually going to redraw the rest of this problem. I'm actually going to redraw this triangle. So now we're working with a triangle here. I need to know the height. We're going to call this A. And then I need to know the side. Well, this is drawn at a perpendicular. This whole angle is 72. Well, here's what I do know. This is an isosceles triangle, and so then that makes each angle congruent. So that cuts this into 36 and 36. So I'm going to pause for a second. I have just given you a ton of information. Now, I know that this angle is 36. I'm trying to find this height, this apothem. Can you think of a way that we can use what we've learned so far about triangles to find this height? If you think you know, pause it, figure it out, try it, and then see if you got the right answer. All right, here's what hopefully you thought of. I can use trigonometry. From this angle of 36, A is our adjacent side, and 10 is the hypotenuse, and so that goes with using cosine. So that means that the cosine of 36 degrees is equal to A over 10. Multiply by 10, that means that A is equal to 10 times the cosine of 36 degrees. So we are going to employ, and I do have decimals up. We're going to employ trig. First thing, we want to make sure that we're in degree mode. I was not, so I click the little menu tool. And we're going to do 10 times the cosine of 36 degrees, and that gives us an apothem of, let's do nearest tenth, 8.1. So A comes out to be 8.1, alrighty. So now we've used trig to find the apothem. I'm going to make this green and move it off to the side. Now my last task is I need to figure out how long this side is. So at this point, what we're going to do is we're actually going to employ the help of trig again. I'm going to call half of the side length x and think of it as part of my right triangle. Now, using trig, this is opposite and 10 is adjacent, so I could now use trig again, but I'm going to use, it's 10 is hypotenuse. I could now use sine. So that means that the sine of 36 degrees is equal to x, which is half of our side length, over 10. So that means x is 10 times the sine of 36, which makes x equal 10 times sine of 36, nearest 10th, 5.9. And then for our side length, that's going to be 2 times 5.9. And actually, for rounding error's sake, I'm going to actually go back. I'm going to multiply this number by 2. That gives us 11.8, which I think would come out to be the same. So 11.8. All right, so we are on a roll. We now know the side length. We know the apothem. We are almost to the place of being able to do our formula. I just need the perimeter. At this point, if you know the side length, you are one step away from your perimeter. How many sides are there? There's 5. So the perimeter is 5 times 11.8. And 5 times 11.8 gives us approximately 59. Now this is where I get uncomfortable with rounding errors because we lost our decimal. It should be 59 point something, but we've rounded, so that happens here. So then now we're finally ready to go. In this space over here, let's do our formula. Area is 1/2 the apothem, which is 8.1, times the perimeter, which is 59. Now at this point, I'm just going to put this whole thing in the calculator. 8.1 times 59, and then I'm going to click divide by 2. And I know it put in a fraction. It's fine. Numbers are all doing the same thing. And to the nearest 10th, ooh, that rounds up. So that's 239.0. So that gives us an area of 239.0 square units. So finding the area of a regular polygon, we have to employ trig, so it's going to be a little bit tedious here as we work this through. So it will take some practice. This will take some time, but hopefully this was a nice example to work through. We're going to work through a couple more here, and then the rest of the examples will be optional as you look to work these through. Example 2. So as we look at example 2, it asks us to find the area of a regular dodecagon if its longest diagonal measures 24. So they give us the shape, they tell us it's a dodecagon, and then they give us one piece of information, longest diagonal measures 24. With this idea here, first question that maybe you're asking is how many sides does a dodecagon have? That is going to impact how we solve this problem. So a dodecagon, if you remember, then hopefully that will help you out from chapter 5. If not, don't forget that Google is our friend. We can look that up. And then hopefully you can find that a dodecagon has 12 sides. So you could try to draw out a 12-sided polygon. That's going to be tricky. So I just went to Google and I found this one. And so here is a dodecagon, 12 sides. So then next up, it tells us the longest diagonal measures 24. So the diagonal crosses from either a vertex or a side to the opposite side. So in this case, the longest one is going to be connecting the vertex through the center to the opposite vertex. So I could draw it maybe something like that. And then this diagonal, the center is in the middle of it, and it does cut this diagonal in half, and those are the two what we've called radii, or the radius of a regular polygon so far. And so that makes each of these blue segments 12 and 12. So that is what we know so far. That 12 is different from just the 12 sides. So we have a lot of 12s here. When we think about the area formula that we've seen so far, the area is 1/2 apothem times perimeter. And so if we think about what we need to find, well, we need to know what the apothem is. We don't know so far. And then we need to know what the perimeter is. And we thus far don't have the perimeter. And then don't forget that in order to know the perimeter, I need to know how long one of the sides is. So that is now 3 pieces of information. So then we want to go back to how we did this in the last problem. What we did is we formed a triangle with the radii. So I'm actually going to draw the other part here to make an isosceles triangle. I know that this piece will be 12. And then the next thing that we did is we figured out, we're going to call this, for the sake of these problems, the central angle. So this angle up here, this central angle, is going to have a measure of 360 over n. And so for our sake, it's 360 over 12, which gives this a measure of 30 degrees. So then next, we drew in the apothem and we split this into 2 right triangles. And so I know that this is A. So at this point, to find A, it's going to be easier to draw, I think, just the diagram that's really complicated because it's a small triangle. So I'm going to redraw the half of it on the side here as a right triangle. So this is A, the hypotenuse is 12. And then we have this angle that's 30, and then the apothem cuts it in half. So that means that the angle up at the top of this triangle is going to be 15 degrees. So then hopefully you remember from before that in the previous problem we used trig. And so now if I want to find the apothem, from the 15 degrees, A is adjacent and 12 is the hypotenuse. So that uses cosine. So that means the cosine of 15 degrees is equal to A over 12. So then now multiply by 12, that means that the apothem is 12 times the cosine of 15 degrees. And let's give it a second here. All right. Let's see, check again in degree mode, 12 times the cosine of 15. And I'm going to keep 2 decimal places just so that we can keep it as exact as possible. I'm going to make this 11.59. And then we need to figure out the length, the whole side length of this triangle. And we figured out that the right triangle contains half of it. So I'm not going to call it S. I'm just going to call this side X. And then we'll multiply X by 2. So now, using the 12 and using the X, that would be sine. So that means that the sine of 15 is equal to X over 12. So X is 12 times the sine of 15. And you're going to start to notice patterns as we work this through. That makes X equal to 12 times the sine of 15. All right, great. And that is let's do 2 decimal places, 3.11. And so that means that up here, the apothem is 11.59. The side length is going to be 2 times 3.11, which is 6.22. And then the perimeter, how many sides do we have? We have 12 sides. So that's going to be 12 times 6.22. So 12 times each side length. And so that makes our total perimeter come out to be, let's see here, 12 times 6.22 is 74.64. So what you're going to notice in these problems is you're going to work through a lot of work and you're going to realize we're still not quite done. We have to figure out the area. So now off to the corner here, our area is 1/2 apothem, which we said was 11.59 times the perimeter, which is 74.64. So now I am going to multiply those. This gives us 11 times 59, or 11.59 times 74.64. Divide that by 2, and that gives us an area of 432.5 square units. All right. For these last 2 problems, these are extra extension problems, and I'm going to work through these, but this is the basics. The basic of working through these polygons. It looks like a lot of work, even going back and even looking at these. The big idea is we're going to break it down into a triangle. The bottom is the side, and we need that side length to find the perimeter. We have the apothem, which is the height of one of the triangles formed, and the sides of the triangles we call radii. We have to use trigonometry to figure out our missing pieces, and then we can plug that in to find our area. So if you feel like you have a good grasp on it, you can go to the challenge problem or go to the practice set. If you want to look through one more problem, I'm going to work through number 3 here, and then the notes key will have number 4 on it as well. So here we go. Number 3 gives us an equilateral triangle ABC. The whole big thing has area of 9√3. A regular hexagon is formed inside so that the side length of the hexagon equals the side length of the equilateral triangle. So that means that this segment and this segment are the same, even if they don't quite look the same, and then for all of our equilateral triangles up here. And so what we need to figure out first is we need to figure out what the length of this side is. We need a number to work with. So if the whole triangle ABC has an area of 9 root 3, well, first I could actually figure out how long this whole side is if I call it S and use the equilateral triangle formula. So we're going to work that off to the side here. That means that 9 root 3, now if you need to go back up in the notes, please do, but our formula is S squared root 3 over 4. So now I'm going to solve this through. So algebraically, I want to get rid of the fraction. We always like to get rid of fractions. So I'm going to multiply by 4. Remember, the 4 only multiplies with the 9. So this becomes 36 root 3 is equal to s squared root 3. Now I can divide both sides by root 3, and the root 3's cancel, leaving us with s squared is equal to 36, which means that the side of this equilateral triangle is 6. How that helps us is that if each of these pieces are equal, then they each have a side length of 2. So then it asks us to find the area of the hexagon. It also asks for the perimeter, and then it asks for the length of the longest diagonal. So let's break this down. I think the easiest to answer is actually going to be part B. What is the area of this hexagon? Well, what is the perimeter? The perimeter has 6 sides, each length 2. So that gives it a perimeter of 12 units. So then next up, when I go to find the area, if I already know that P is equal to 12, the only thing that I need is, I don't know why I wrote 6 there, is the apothem or the apothem. So I go up to my hexagon, and I draw in the radii, and I know first that the side length is 6. So now next up, I'm going to shrink this because it looks very large right now. All right, so next up, we find our central angle. So the central angle of this isosceles triangle is 360 over n, so 360 divided by 6. That gives us an angle measurement of 60. So then next up, I drop in my apothem, and then something interesting happens here. When I cut it in half, this angle measurement is 30 degrees. Maybe this is starting to ring a bell. This is going to make it a 30, 60, 90 triangle. This angle at the bottom has to be 60 degrees. So I could use trig. That's fine. You'll get the decimal equivalent, but we could also use a 30, 60, 90 triangle. So that means that because the side length of 6 for the whole triangle gets cut in half, it gets cut in half, then this side length, it's not liking this right now, there we go, its side length is going to be 3. Then for this length of 3, that's across from 30. So that's our x. So that means that the apothem is x root 3, so that makes it 3 root 3. So that makes our apothem 3 root 3 using 30, 60, 90 triangles. So that means that the area of our hexagon is 1/2 of 3 root 3 times our perimeter of 12. Keeping it exact here, that gives us half of 36 root 3, and then half of 36 is 18, so that gives us an area of 18 root 3. And then lastly, the longest diagonal, it always connects your opposite vertices. Since this triangle has it's got two 30, 60, 90 triangles in it, that makes it an equilateral triangle. And so that means that, I know this diagram is a little crazy right now, but with this diagram, all the sides are 6, which means that my radius is also 6. So I just need to double that for my diagonal. So my diagonal is 2 times 6, so my diagonal is also 12. So hopefully this example here helped. If you're interested in seeing another example, the answer to this is on the key that is posted in Schoology. All right, on to the practice. Let me know if you have questions.